Hello. Today I want to talk about some of the stormwater management innovations occurring in Madison. We know that urbanization alters the hydrologic regime of urban areas. The introduction of impervious elements such as rooftops, driveways, sidewalks, and roads reduces the amount of infiltration and increases the amount of stormwater runoff. This infrastructure also creates more efficient drainage pathways, both of which create a more flashy hydrologic regime with greater volumes of stormwater runoff and higher peak discharges. Traditional stormwater management practices try to ameliorate this situation by introducing gray infrastructure, such as stormwater detention ponds, which, by creating temporary storage, uh, detain or slow down some of this runoff. This also allows some of the sediment and nutrients to be removed from the water, protecting some of our downstream receiving water bodies. We can also introduce infiltration practices. These include retention or infiltration basins or bioretention basins, which include engineered soils. The water flows into these facilities and then is retained when it infiltrates into the subsurface. So these can reduce the volume as well as pollutant loads in stormwater runoff. So if we have our altered hydrologic regime that has resulted from urbanization and we introduce detention ponds, we can change the timing and the peak concentration of the discharge. In addition, if we introduce retention features, we can change the total volume of runoff. Combined, these create a more natural hydrology. Here in Madison, we not only have these more traditional stormwater management infrastructure in practice, but also a lot of innovative techniques. So I want to spend today showing you some of those innovations. And so we have our stormwater management tour guides here. Moving from left to right, we have Carolyn Voter, who received her PhD from our program and now works with the Wisconsin Department of Natural Resources. We have Steve Gatfield, who also received his PhD from our program as a professional engineer working for EOR, which is a consulting firm in the upper Midwest and has an office here in Madison, which Steve leads. Phil Gabler, who is also an alumni of our program, and he's a water resource engineer for the city of Madison. And then yours truly. So what we're going to do today is give you a tour and show you around some of the green infrastructure that has been implemented here in the city. Today I am in the Westmoreland neighborhood, about a mile and a half down the southwest commuter bike trail from Engineering Hall. And this is the site of a road and infrastructure reconstruction project with a green infrastructure study. The purpose of this project is to use green infrastructure to reduce the volume of runoff generated in this neighborhood and to measure it at the neighborhood scale. First, the city is using innovative green infrastructure technologies to disconnect impervious areas, roofs, and driveways and streets from the stormwater sewer system. They're doing that through installation of permeable pavement, introduction of rain basins, rain gardens, and rock cribs. Secondly, they are incentivizing homeowners to implement green infrastructure on their property. That also includes rain gardens, rain barrels, and green roofs. And third, the city has teamed up with the USGS to measure the stormwater runoff generated from this neighborhood both before and after these interventions. Phil Gabler from the City of Madison Engineering will show us some of the work that the city's been doing and also talk about some of the challenges that they've encountered along the way.
Hi everyone, my name is Phil Gabler. I'm a water resources engineer at the city of Madison, and I'm out on our first permeable street that we've ever built in Madison, and I'm just going to tell you a little bit about that today. So the section I'm in right now, this is on St. Clair Street over by the Glenway Golf Course, and we have a 5.5 foot wide strip of a product called Pave Drain. This is a 1 foot block, and the block here is not permeable, but the gap around it is. Underneath this block is a foot of 57 stone, so that's 1 inch clear stone, no fines. There's a geogrid on top of that, and then there's below it 3 inch clear stone down to the sand layer. On this project, that's 10 feet below, which caused a few problems with sewer lateral interference and other things, but we needed to get down to that sand layer for this to function. Something else you'll see here, which was a learn on the job, is this is machine poured curb. They use a curb machine that goes along and slides a form through the concrete. There's some wobble in that, but there isn't wobble in the paver. And so we ended up having between a 1/2 inch and a 1.5 inch gap here, which was not safe. We were gonna fill it with chips, but then when we vacuum this, it will suck the chips out. So we put polymeric sand in here instead, which is hard like concrete, but pours in and isn't sloppy. So that's how we solved that problem. We also had issues with these pavers being too high, and we ended up coming in and using wood to go across the side and put a vibratory compactor on a front end loader and put a lot of weight on this. So that was able to move these down to within a 1/2 inch of the curb line. We were hoping it was going to be raining today, but it's not. So we aren't going to get to see this in action. But now we're going to go up the hill and see the permeable concrete panels that we put in as well. All right, so we've moved up the road a little bit, and on this project we are comparing the kind of the longevity of pave drain and pervious paver panels. So this is a product, this is a precast pervious concrete made by Spancrete, and they make this inside of a factory where they control the environmental conditions. And they come in these 5 foot wide sections that snap together kind of like Legos. So this has the exact same base where we have the open stone and then the 57 stone and then a geogrid, and then we laid this right on top of it. And this is, there's tongue and groove going one direction and then little tabs on the other side. We'll see how these two hold up. This one is much more prone to having spall, and you can see there's some little chunks that come off, but we're hoping that it will hold up over time and not crack. All right, so one other additional thing we did with the pervious concrete panels is we replaced some sidewalk. Now this sidewalk is placed in between a resident's driveway and the street. This is the directly connected impervious. That's a target of our study, because that's where we think we'll get our highest reduction in that peak runoff for small storms. So you can see here we had a problem in that the driveway was not perfectly flat. This was not something that we thought was going to happen. And so in order to match the grade of the driveway in with the perfectly flat panels, we had to cut into the resident's driveway. Thankfully they gave us permission, and re-pour some concrete to match that edge. Now as water comes off of the driveway, it goes into the pervious concrete sidewalk, and underneath here we have a under drain that connects it to a 5 foot by 3 foot deep minimum by 15 foot long rock crib. Here this goes down to that sand layer, so I'm on 10 feet of stone. So any water that comes off that driveway is going into the ground. And then, if it fills up before it goes into the base course of the road, there is a 8 inch under drain that connects into that inlet there.
Another common form of green infrastructure that I'd like to show you is a rain garden. If you can imagine runoff being generated from the road and flowing down this gutter, you see that as it would flow down, it eventually hit this cut in the curb. And it would flow into what now is a depression, and will remain a depression, but will be vegetated with native plants. This will allow an opportunity for storage of excess water and allow for infiltration into the system. Hello, here I am in a rainstorm over by the UW hospital, and I want to show you some green infrastructure in action. So we can see that we're getting quite a bit of runoff here from the road. That runoff is heading down here, and some of it is going into our rain garden. Some of it's bypassing going into the storm sewer. We're filling up the rain garden a bit. And if this gets full enough, we have an overflow over on that side, which also drains to the storm sewer. If we take a look, here we have a rain garden. What the rain garden does is it captures water from the roof, which comes down downspouts and rain chains, and is collected through piping and fed underground into the rain garden, where it accumulates and eventually infiltrates.
Hi, this is Steve Gaffield, the Water Resources Engineer with Emmons and Oliveira Inc., or EOR, based in Cottage Grove. And I'm here at beautiful Warner Park in the city of Madison. And the city of Madison hired us about 2 years ago to do a stormwater study to address some typical urban stormwater problems that this area that's much loved by the neighborhood for its wildlife and fish suffer from. It's got an urban watershed, lots of sediment, phosphorus loading. It's become hyper-eutrophic, lots of algae blooms, lots of fine floating plant growth, duckweed, and that has led to regular dissolved oxygen crashes, which then leads to fish kills. And the one fish that survives really well in these conditions are carp, and a lot of carp get into this lagoon from Lake Mendota. So this required looking at stormwater as an integrated water quality and biological system. One of the recommendations here was install a simple Great Barrier between the lake and the lagoon, help keep some of these carp out. Reduced carp activity means fewer of these bottom-feeding fish ripping out aquatic plants and stirring up sediment, which leads to high turbidity. So if you can reduce that, make the water clearer, more sunlight penetrates, more aquatic macrophytes can grow. These things are valuable for bluegill and other panfish habitat. They have a natural algae bloom suppression action. They can take up nutrients and help sediment settle. Another recommendation is to install some stormwater treatment wetlands at major sewer pipe outfalls into the lagoon. They work much the same way in a more engineered, focused area. Provide some settling, provide nutrient uptake where water would have to flow through an engineered pool that's an open marsh setting. Plants can help mechanically filter and take up nutrients. And the upshot is, if you look at this as an integrated system, there's an opportunity to really make a difference to water quality here in the lagoon and downstream in Lake Mendota.
So what my work highlights is that there are small areas within a parcel that do most of the heavy lifting in terms of infiltrating runoff. And those places are the interfaces between impervious areas, so walkways, driveways, patios, and especially roofs, and pervious areas, so basically the yard. And anywhere that runoff from impervious surfaces is routed to pervious areas and is able to infiltrate really well can be a hot spot in terms of reducing runoff. So what I encourage homeowners to do is three things. So first, identify those impervious pervious interfaces, so those places where impervious areas are adjacent to the yard. And then second, look for ways to adjust the way that water flows so it's flowing from the impervious surfaces to the yard. One of the easiest and also most effective places to do this is via downspouts. So in some older cities, it's common for downspouts to disappear into the ground and have a direct and piped connection to the sewer network. In other cities, including here in Madison, downspouts can still be effectively connected to the sewer network because homeowners can sometimes route them so that water flows to the driveway, down the driveway, into the street, and into the sewer network from there. So once you've identified where you have these impervious interfaces, make sure that water is actually flowing from the impervious areas to the yard. And then lastly, make sure those locations within the yard actually do infiltrate water. So it's common for our urban soils to be highly disturbed and compacted, and they may not be functioning all that differently from impervious surfaces themselves. So if that's true of your yard, and you can test this using a simple single ring infiltrometer, be sure to amend the soil at the interface between the impervious and pervious surfaces by replacing the soil or mixing in some kind of sand and compost mixture. And even doing this for a fairly small area, say a 5 foot by 5 foot by 1 foot deep area at the downspout outlets, can make a really big difference if the soil is really badly compacted.
Well, I hope you've enjoyed our tour of green infrastructure in Madison. If you keep your eye open on campus, you're sure to see a lot of other green infrastructure, including a few green roofs, such as this one on the new education building. I'd like to thank our tour guides, Steve Gaffield from EOR Inc., Carolyn Voder from the Wisconsin Department of Natural Resources, and Phil Gabler from the City of Madison Engineering. They've shown us how consultants, the government, and the public are working together to make a more seamless and sustainable connection between the built and natural environment.